Ever get that feeling your favorite online store is, I don't know, reading your mind? Or you notice that peanut butter is always suspiciously close to the jelly in the supermarket? Well, it's not magic. The answer is hiding in plain sight, buried in trillions of bytes of shopping data. Okay, let's dive in and unlock the secrets behind the algorithms that turn your shopping cart into some seriously powerful insights. So, this whole thing really kicks off with what we call the market basket model, and a story that's become a legend in data mining. You've probably heard it. The tale goes that a big retail chain discovered that on Friday nights, guys buying diapers were also incredibly likely to grab a six-pack of beer. Now, who knows if it's actually true, but honestly, it doesn't matter. It perfectly captures the goal here, finding these surprising, super useful connections in just massive piles of data. And that, right there, is the heart of association rule mining. So here's the game plan for our journey today. We're going to start by actually defining what a rule like diapers and beer means. Then we're going to smash right into the computational brick wall of trying to count everything. From there, we'll meet the hero of our story, the a priori algorithm, see how the PCY algorithm made it even faster, and wrap up by looking at how sometimes being smart with sampling is way better than being perfect. All right, first things first. Before we can go digging for gold, we've got to learn the language of the trade. Let's break down the key terms that data scientists throw around when they're talking about these hidden patterns. At its heart, an association rule is really just a simple if-then statement. So a rule like diapers, milk implies beer is just our fancy way of saying if a shopper buys diapers and milk, they're probably going to buy beer too. Seems simple enough, right? But the real trick isn't just finding rules. It's finding the good ones, and for that, we need a way to measure them. And our first and maybe most important yardstick is support. The easiest way to think about support is just popularity. How often does this combination of items actually show up? So the support for diapers, beer, is literally just the fraction of all shopping carts that have both diapers and beer in them. We always set a minimum support level to just filter out all the random, rare stuff that doesn't really matter. Okay, next up is confidence. Now, if support tells us how often a combination appears, confidence tells us how reliable the rule is. Don't let the formula scare you. It's actually pretty intuitive. It's just the popularity of everything together divided by the popularity of the if part. Think of it like this. Of all the times someone bought diapers, what percentage of those times did they also buy beer? That's confidence. It tells you if the connection is real or just a fluke. Now, here's a crucial point. When you run these algorithms on real data, you can end up with millions, sometimes billions of rules. It's a total flood. We need ways to trim the fat, you know? This slide shows two really smart ways to do that. First, you have maximal item sets. Think of these as the biggest possible popular combinations. They're frequent, but if you add even one more item to them, they become unpopular. Then you have closed item sets, which is a little more subtle. This is a frequent set where adding another item always changes the support count. This is great because it gives us the exact frequencies without having to list every single little subset. Both are just clever tricks to get to the good stuff without drowning in noise. And this brings us to the central problem of this whole story. Finding these patterns seems so straightforward, but when you're working with millions of items and billions of shopping carts, you hit a computational nightmare. Yeah, let's just put the question out there. We're just counting things that show up together. How hard can it possibly be? Turns out, the logic isn't the problem. It's the unbelievable, mind-boggling scale. The most obvious brute force way to do this is what we call the naive algorithm. It's super simple. You go through every single shopping basket. For each one, you look at all the items and you generate every possible pair. Then you just add one to a counter for each pair. It works. It gives you the right answer. But, oh boy, does it have a fatal flaw. And there's the fatal flaw. 2 terabytes. If a store sells a million different things, which many do, just to create a space in memory to count every possible pair would take about 2 terabytes of RAM. I mean, it's beyond impractical. It's impossible for pretty much any computer on the planet. So what do? Well, there are a couple of ways you can try to store these counts. The first approach, the triangular matrix, is the one that takes up all that space. It basically pre-allocates a little box for every single possible pair, whether it shows up at all. The second approach is a bit smarter. It only creates a record for pairs that have actually appeared in a basket at least once. This is definitely better if most pairs never show up, but it still doesn't solve that fundamental memory crisis when you're dealing with big data. So how did we get out of this mess? How did computer scientists crack this seemingly impossible problem? Well, it was with a truly beautiful, elegant algorithm called a priori. This was the breakthrough. This is what made it all possible. The absolute genius of a priori comes from a really simple, common sense idea. It's a principle called monotonicity, and it just says this. If the pair diapers beer is popular, then just diapers by itself has to be popular, and beer by itself has to be popular too. You can't have a popular pair made of unpopular items. So the algorithm does this in 2 passes. In the first pass, it doesn't even look at pairs. It just counts individual items and makes a short list of the frequent ones. Then, in the second pass, it only bothers counting pairs where both items made it onto that first list. It's a brilliant filter. And this picture shows exactly why that's so smart. In that first pass, you only need a little bit of memory to count the individual items. Once you have your frequent list, you can just toss those counts. Then, you reuse that same memory for pass 2 to count only the much, much smaller group of candidate pairs. It's an incredibly efficient way to use our resources. Okay, let's walk through this example to see it in action. Let's say our support threshold is 3. In pass 1, we count all the individual items and find that only B, C, J, and M appear 3 or more times. That's our frequent list, L1. For pass 2, we only form pairs from that list, so we get the candidates in C2. We count them and find the frequent ones, which gives us L2. Finally, we look at L2 and realize the only possible frequent triple we can make is BCM. We count it, and yep, it's frequent. See how at every single step we're massively cutting down the number of things we have to worry about? A priori was a complete game changer, for sure. But the story doesn't stop there. You know how researchers are? They looked at this beautiful process and said, I bet we can make it even faster. This quote right here from the creators of the PCY algorithm nails it. During that first pass of a priori, you're only counting individual items. That doesn't take much memory at all, which means you've got all this other RAM just sitting around, doing nothing. The PCY algorithm cleverly puts that idle memory to work. So here's the trick. During that first pass, while you're counting the items, you also look at all the pairs in the basket, but you don't store them. Instead, you run each pair through a hash function, which just turns the pair into a number, like a bucket number, and you just add one to a counter for that bucket. At the end of pass 1, you look at your buckets. If a bucket's count is below the support threshold, you know that any pair that hashes to that bucket can't possibly be frequent. So for pass 2, you have a new rule. A pair is only a candidate if both its items are frequent and it hashes to a frequent bucket. It's this powerful extra filter that makes pass 2 even faster. So far, we've been obsessed with getting the exact 100% correct answer, but that requires multiple passes over the entire dataset. What happens when your data is so big that even 2 passes is just too slow? Well, this is where we have to shift our thinking, from perfect accuracy to practical efficiency. The big idea here is sampling. It's pretty simple. Instead of reading your entire 10 terabyte dataset, what if you just read a tiny random 1% sample of it? You can run a priori on that little sample in no time. Whatever's frequent in that sample becomes a candidate for being frequent in the full dataset. The SON algorithm takes this idea and runs with it. It breaks the data into chunks, finds candidates in each chunk, then combines all those candidates into one big list. Then it just does one final pass over the full dataset just to get the true counts for that much smaller list. It's a fantastic way to find most of the answers way, way faster. But what if you could get the best of both worlds? The exact answer, but with a really high chance of only needing 2 passes. This is where a truly mind-bending idea called the negative border comes into play. Think about it. When you take a small sample, what are you most likely to miss? Not the super popular stuff. You're going to miss the items that are right on the edge, the ones that just barely miss the cutoff in your sample. The negative border is a formal way of finding these almost frequent sets. These are the sets we need to be paranoid about. Let's make this concrete because it's a little tricky. Let's say the set A, B, C, D is one of our troublemakers. It's on the negative border if it was not frequent in our sample, but all of its smaller 3-item subsets like ABC and ACD were frequent. So in its second pass, Toivonen's algorithm counts everything that was frequent in the sample plus all of these special negative border sets. And here's the magic part. If none of those negative border sets end up being frequent in the full data set, we're done. We know with 100% certainty that we found the exact complete answer in just 2 passes. It's brilliant. And that really leaves us with this final big question. We've gone from a simple idea that was totally impossible to a whole series of incredibly clever algorithms that play this game between accuracy and speed. But as our datasets just keep growing to a planetary scale, we have to ask ourselves, Is the future of data mining finding these perfect, exact patterns? Or is smart, fast, good enough approximation the only way we can possibly move forward?